Assalamu alaikum everyone. This is tutorial video for chapter 4, and in chapter 4 we have done some applications of derivative and problem related to increasing and decreasing function, local extremas, and concavity and curve fitting, and in the end we have done some optimization problems. So I will pick some problems, and this is the first problem, in which we have to find the local extremas using first derivative test. So this question maybe we can attempt by using the second derivative test, but we have learned in the class in some cases the second derivative test fails. So it is, and also there is another reason why I have used first derivative test to compute the local extremas is in this method we learned the how to compute the critical points, and the second thing we learn in this method is how to compute the intervals where function is increasing and decreasing, and in third, when we are done with these two, we will compute local extremas. So let's start. The first thing we need to compute is the derivative of this function, and that is for critical points. And before differentiating this, I will rewrite it. This is f of x, and we can rewrite it like when we multiply this with this, it will become 2 by 3 x power 1. So I will write it directly here, powers add. So this is 1, and then plus 5x power 2 by 3. So this will give us x power 5 by 3 and plus 5 x power 2 by 3. Now we differentiate this function, and when we differentiate this function by using power rule, it will give us 5 by 3 x power 5 by 3 minus 1 and plus 5 into 2 by 3 x power 2 by 3 minus 1, and after simplification, if we take 5 by 3 and 5 by 3 common, it will give us x power, this become 2 by 3 after simplified this fraction, and plus 2 x power. By simplifying this, we will get minus 1 by 3. Okay, so we also can write this in the form of this is x power 2 by 3 plus 2 by x power 1 by 3. So when we move this into the denominator, this power will become positive. And now for critical points, we need to compute the where the derivative, we recall what was the definition of critical point is the we need to compute where the function's derivative is 0 and where the function's derivative is undefined. So let's make it more simpler, because it is easy to compute the critical points, because 5 by 3, and when we take LCM, it will give us x power 1 by 3, and this is 2 by 3 plus 1 by 3. We know how to compute the LCM, and after that it will give us x plus 2 by x power 1 by 3. So now we have to check where the function is 0, for what values of x the function is 0, and for what values of x the function is undefined. So if we see, if we place x is equal to 0, this function will become undefined, and there are other methods that how we compute these things, that if we write it x power 1 by 3 is equal to 0, this will give us x is equal to 0. So this is the point where the function's derivative is undefined, and the second one is where the function's derivative is 0. When we place minus 2 here, this will become 0. So we will place numerator is equal to 0, and from this we will get x is equal to -2. So here we have two critical points. Now we are done with the first step, and we need to move on to the second one, in which we have to check the increasing and decreasing function. And for that we need to compute the intervals of increasing and decreasing function, and we know that how to compute the intervals when we have the critical points. So by using critical points, let's draw a real line. Here we have 0, and here we have -2. And when we compute the intervals, the first interval we will get is from this is when we extend this is minus infinity, and this is plus infinity. And the first interval we will get from here is, let's make a table. So the first column is for intervals. The first interval is from minus infinity to -2. The second interval is from -2 to 0. And the third interval is from 0 to plus infinity. Okay, so here we have three intervals, and the next step for increasing and decreasing, we are take some test values and put these test values into this derivative, which is 5 by 3 and x plus 2 by x 1 by 3. So here we have the derivative of the function, and now we will pick some test values from these intervals and put them here to compute the signs of this f dash. So if we get positive sign, this will tell us that the function is increasing, and if we will get negative sign from the test value, this will tell us that the function is decreasing. Okay, so let's start. When we pick -3 from this interval and put in this, because this thing we need to compute in this portion, and when we pick x is equal to -3 and put it into this derivative, this will give us -3 plus 2 by -3 power 1 by 3, and we'll get minus from here and minus from here, and this will become positive. So this will tell us that this interval is positive. So it means that our function is increasing in minus infinity to -2 interval. Okay, so the next thing is we need to compute the next value, and next value is we can take -1, and when we take x is equal to -1 and put it into this f dash, we will get -1 plus 2 divided by -1 power 1 by 3, and we will get plus from here and minus from here. So the final answer is negative, decreasing in -2 to 0. And the last one is from 0 to infinity, plus infinity, and let's pick a positive one from this interval. And when we pick positive one, it will give us positive 1 plus 2 by 1 power 1 by 3, and we'll get positive from here and positive from denominator, and the final answer is positive. So this means that the function is increasing into this interval. Okay, so this is it. We are done with increasing and decreasing, and now we are moving to the next part, which is the local extremas. And we have learned in the class, if our function, because this is a real line, we are making that if our function is positive in this interval, the derivative is positive in this interval, and function is increasing in this interval, this means that the function is increasing and this interval, and the next one is decreasing and this interval, and then increasing in this interval. So this will tell us that our local extremas are at -2 and 0, and when our function is increasing and then decreasing, this will tell us that we have shape like this, and here we have the local maximum point. So we can say that the function f has local max at x equal to -2. And similarly for the next interval, where we have from -2 to 0, our function is decreasing, and then from 0 it is start increasing, so it will become shape like this. So this tells us that our function is has local minimum at this point, which is 0. So we can say that f has local minimum at x is equal to 0. And if you want to compute the exact point, you can put this x into this function, and this will give us the exact coordinates of local maximum and local minimum. So this is it for question 1. So this is question 2, and this is from section 4.5. We need to evaluate this thing, and in section 4.5 we have learned that how to compute limits using L'Hopital rules. So what was the L'Hopital rule? When we have limit x approaches to a f of x, and we encountered with 0 by 0 or infinity by infinity form, it can be rewrite into f dash of x by g of x, and this is only when we have 0 by 0 or infinity by infinity form. So let's try to solve this question, and we cannot see here the f by g form. So for directly, if we apply directly limits, let's sort the solution. And when we directly apply the limits, before applying the limits, let's rewrite it. We can rewrite this thing x plus 2 in this form, and this thing is in this form on power x. And now when we apply the limit directly into the function, it will give us 1 plus, this will give us 0, and 1 minus 0, and power infinity, and by simplification it will look like this. So now we have an indeterminate form of 1 power infinity, and we have learned in the chapter in section 4.5, whenever we have encountered these type of forms where our infinity is in the power of something, we will take our function. Let's let f of x is equal to x plus 2 by x minus 1 power x, and in the next step we will take logarithmic onto the both sides, and then we are able to move this x from here to the start of the function by using logarithmic properties. And this we can write in natural log of f of x is equal to x natural log of x plus 2 by x minus 1. So now if we again, if we try to evaluate the limit in this form, this will give us infinity into 0 form, because here we have 1. So we have solved here, this will give us 1, and natural log of 1 is 0, so this will give us infinity into 0 form, because natural log of 1 is 0. So these type of forms we know how to compute. If we have situation in like this, we can rewrite this function, like natural log of x plus 2 by x minus 1 divided by 1 by x. So we can rewrite this function into this form, and if we apply limits, this will give us 0 by 0 form. Okay, so now we can apply this L'Hopital rule over here. But for L'Hopital rule, we need to take the derivative of this function, these two functions, and when we take the derivative of this function, let's rewrite it again. We can rewrite this function by using logarithmic properties: x plus 2 minus ln of x minus 1 and by 1 over x. So now this is our function, and apply the limits on both sides. X approaches to infinity, natural log f of x, this will equal to the limit x approaches to infinity. And now take the derivative of this function. Let's write it first, x in proper form. One by x. Now when we apply the limits, we will get a 0 by 0 form. So by L'Hopital rule, we can write this thing as limit x approaches to infinity, and when we take the derivative of this thing, it will give us 1 by x plus 2, and into the derivative of this is 1, so we will write 1 here, minus what is the derivative of this is x minus 1, and the derivative of inner side is 1, so this is it. And after that we will compute the derivative of the denominator, which is 1 over x. When we move it in the numerator, it will give x power minus 1, and by power rule this will give minus 1 by x square. Okay, so this is it. We have differentiated these two functions, and let's write it in, we can write it in 1 over x plus 2 minus 1 over x minus 1 by minus 1 over x square. So now let's take LCM of these two functions, so we will get a proper form, so we easily apply the limits. So when we take LCM, it will give us x plus 2 into x minus 1, and here we have fx minus 1 minus x minus 2 by minus 1 over x square. So limit x approaches to infinity, and we have this x is cancel out with this one, and we are left with minus 3 by x minus x plus 2 into x minus 1 by minus 1 by x square. Okay, so we can rewrite it x approaches to infinity. This x will goes in the numerator, and this minus will be cancelled out with this one, and this is become 3x square by x plus 2 into x minus 1. And further by solving it, it will give us x approaches to infinity 3x square, and when we multiply these two, this will give us x square plus this will give us plus 1 minus 2. So now this is the final form. So now we need to compute the limit. When we apply directly limits, we will get infinity by infinity form. We either use, because we know now L'Hopital rule, we can apply this rule, or if um, other methods which we have learned in chapter uh, 2 or 1, we can also in chapter 2 we have learned other methods to compute if we have situations like infinity by infinity. So we'll apply the L'Hopital rule, and then it will give us this form. So it will give us limit x approaches to infinity natural log f of x on this side, and on this side it will be limit x approaches to infinity, and this was 3x square by x square plus x minus 2. Okay, so now we are encountered with this infinity by infinity form. So let's apply L'Hopital rule. So it will give us 6x by 2x plus 1, and when we apply limits again, this will give us infinity by infinity form. So by L'Hopital rule, we can rewrite this into x approaches to infinity and 6 by 2, which is limit x approaches to infinity 3. So this is a constant number. When we apply limits, this will give us 3. Okay, so the final thing is we have x approaches to infinity natural log f of x is equal to 3, but we need to compute the limit of f of x. So we know the theorem: if our limit f of x, limit natural log of f of x is something, we can write it into x approaches to infinity f of x e power 3. So this is our final answer. So this is how we can compute limits of these type of function using L'Hopital rule. So here we have. So in question 3, we need to calculate the volume of right circular cone which can be inscribed in the sphere, and the important thing is we need to find the maximum volume or largest volume of that cone. So this is from applied optimization. This question is from applied optimization, and in applied optimization we have learned that whenever we have some problems of applied optimization, we are try to draw those problems to for better understanding. So let's uh, draw a sphere. So this is a sphere, and let's make a rough sketch of a cone which is inscribed into this sphere, and this is the cone. Okay, so what is the volume for the cone is V is equal to 1 by 3 pi r square h. So here we need r and h, but we are only given the radius for the sphere. We are not given the radius for this cone or height for this cone. So let's say that this line represents the radius of this sphere. Okay, so this is, we can say that this is 3, and if we draw a line from this point to this point, the height for this is also 3, and but we need to have the complete height, which is from this point to this point. So let's say that the height of this is 3 plus this thing. Let's say we can say this is y, and but we also need the radius. So let's say from this point, this is the radius for cone, this point to this point, this is the radius, and this is the radius for cone. We can say that this is x. Okay, so Now we can write this uh, whole problem into um, if we try to write, this is 1 by 3 pi, and this is x square, and this is this complete height is 3 plus 3 plus 3 plus y. Okay, so but this is a function of two variables. We need to compute a single variable. We need to convert it into a single variable. So how to compute this whole function into a single? Let's find by using Pythagorean theorem. We can compute by Pythagoras theorem. We can compute this x, because this is a 90-degree angle. So our x will be, x is equal to, or x square is equal to 3 square minus y square. Okay, so this is our x, and we can compute this is our x square, and if we want to check what is the height for, what is the value of x, we can take the square root, which is 9 minus y square. Okay, so we are able to convert this whole function into one single variable, which is y, and 1 by 3 pi, because this is x square, so we can write 9 minus y square here, and this is 3 plus y, so this is our function. And one thing which is left is we need to compute the domain for this function. So if we take y, what is the domain for y? As this is the height, so we can start it from 0, and uh, from 0 we can take it because if we exceed from 3, this is not this is become the circular cone, which is out of the sphere. So we are bounded with 3, and when we take 3, this whole thing will become 9, and this will become 0. So we cannot take 3, so our domain is from 0 to 3. So this is important, because when we further solve it, we need to find the critical points, and then we need to check whether our critical points in our domain or not. So the next step is we need to check the maximum value of this function. We know how to compute the maximum values. We will differentiate this function with respect to y. This will give us 1 by 3 pi, and if we rewrite this thing into, this will give us 27 minus plus 9y minus 3y square and minus y cube. So now it is easy to solve, and when we differentiate this will give us 1 by 3 pi, and the derivative of this thing is 0 plus 9 minus 6y minus 3y square. Okay, so this is our derivative, and for critical points we need to, for critical points, we need to put this v dash of, sorry, this is function of y, so this is v dash of y is equal to 0, and when we put this thing equal to 0, this is 9 minus 6y minus 3y square, and this is equal to 0. So this is now a quadratic equation, and we can solve this by using quadratic formula or some other formulas. This will give us the values for the y, and I am writing the values for the y are values of the y are 1 and minus 3. So these are the values, but we can see that these are the critical points where this function is maybe have absolute maximum or absolute minimum, but this 3 minus 3 point is out of our domain, so we will take this only one, and we will put this one into our function to obtain the maximum value. So let's plug this one into Vy. So this will give us 1 by 3 pi and 9 minus 1 into 3 plus 1. Okay, so by simplifying it, we can get pi by 3. This is 8 and 4. It will become 32. So our maximum volume is 32 pi by 3, which is on 1. Okay, so this is it.